basically it's a numerical method that has taken some time to get into sort of an engineering tool. It's not quite an engineering tool yet. We hope it'll be an engineering tool very shortly. And so this talk is going to be a little bit interesting because it's going to be sort of my journey into SPH and what we've been doing with it. And so I'm going to talk a little bit about smooth particle hydrodynamics in terms of the theory. So there'll be 3 or 4 slides about where it comes about. So you should have some familiarity at the end of that. I'm going to talk about this physics model, which is our first open source model. And all of this stuff I'm going to talk about is open source. So if you want to try it, it's out there. Our rationale is that SPH takes a while to code. It took us a couple years to code it up right, and there's no point for other people to have to do the same thing we did already. So it's out there, it's free to use. But physics was our first release, and then GPU computing came along, and so now we have a GPU version. And so I'm going to talk about those codes, but mostly I'm going to talk about examples. So you'll see the kinds of things we can do with it, and what's the advantage in free surface flows about using SPH, and then what's the advantage of using GPU computing. So the idea is we have, you can think about smooth particle hydrodynamics as either a mesh-free numerical method. So you can think about these points as nodes. They're just irregularly spaced nodes. So instead of finite difference or finite element and looking at your nodes, these nodes are just irregularly spaced. So you can think about it that way. The only difference is these nodes are going to move with the fluid. So they're Lagrangian. It's a Lagrangian method. So you'll see the nodes moving. And so then a lot of people say, well, then they're like particles of fluid. And so you can think about them as particles or big blobs of fluid moving in the flow, obviously. The way I'm going to talk about it is I'm going to use a weakly compressible fluid model. You don't have to. You can do an incompressible model. It just turns out that when people started doing SPH, it was a lot faster to do the weakly compressible rather than incompressible. But nowadays, it's probably the same amount of computational effort either way. One of the key things about smooth particle hydrodynamics is the idea of a kernel. And it turns out that when you're doing these kinds of particle methods, that a particle or a point at this location, if you want to know, say, the velocity or the pressure or something, you can just sample all the neighboring points in a weighted average, and that gives you the value at that point. It's like moving least squares. We do like a least squares fit here or least squares fit here, and that gives you the value at different points. And in fact, half of SPH is just interpolation. So we're going to talk a little bit about the kernel function. Basically the weighting. If I want to know the value of the velocity here, since this is a closer point, it gets a higher weight. If a point is way out here, it gets a very low weight. And so that's how that averaging is done. This was originally invented in astrophysics. Lucy in 1977 and Gingold and Monahan in 1977. So Lucy was first. Gingold and Monahan almost immediately afterwards developed this for astrophysics. So you can think about a bunch of particles being stars, and then you look at stars interacting through gravity, and then another cluster of stars over here, and you can slam one galaxy into another galaxy, or you can slam a meteor into a planet and so forth. So it's been around for a while, a long time. See, with my new gadget, I have a nice green dot. So, and Monahan said, well, let's just think of this like as if we had a delta function. So mathematically, if we have A defined over a field and we integrate over the domain, and this is a delta function, then we exactly get back A at the point R. So the delta function is at location R. And so he said, well, this is an exact representation. So the only difference is that instead of a delta function, and since we're using a digital computer, we can't, use a delta function. So we'll use this top hat this Gaussian function that looks like a delta function. And we can't do an integral on a digital computer. We'll do a sum. So we'll sum the particles around a particular point. So we have a point R. We want to know what A is. We're going to sample all the neighboring particles, all the different RJs. We use this weighting factor, just sum them up. And so that's the digital equivalent of this exact integral if this was a delta function. So, but it's not. Another way to think of it in this form is if you use other numerical techniques, you can think of this product of the weighting function and this volume element, which I replaced by mass over density since it's a compressible fluid. This is my volume element times the weighting function. You can think of that as a basis function. And so we just have a basis function, like in Fourier series, you have sines and cosines and a bunch of coefficients. These are constants. So each particle has a value of A, and we have this basis function. We sum them up, and we get A at a point. So that's the idea of the interpolation and how it works. The nice thing about it, this is basically the same equation. The nice thing about it is when you want to take a gradient. So if you think about irregularly spaced meshes and you want to take a gradient and you're using finite difference and the particles are all over the place, and finite difference is pretty tricky to do in 3D. Here, you take the gradient of A. Well, this is a constant. This is the value of A on each particle. It's just a number. This is an analytical function. This is a volume element. In fact, we keep the masses all constant. Density is changing, so that changes volume. But the only thing that really depends on R is this function. So when I take a gradient, I actually take the gradient of this Gaussian function, and I know that. That's analytical. So all my gradients, all my derivatives are analytical. So I don't have to do finite differences and calculate all the distances and divide and so forth. It's analytical. So that saves a lot of time, and it's more accurate. Okay, so getting close to the end of the theory slides, we have conservation of mass. Because it's a compressible fluid, mass is going to change because the density of the particles are going to change. But I fixed the mass of all the particles to be constant. So actually, if I just don't lose any particles, I conserve mass identically. But I want to keep track of density as well. So I have a conservation of mass equation. Compressible form looks like this. It's a Lagrangian method, so I don't have convective acceleration. So it's the total derivative of the density with time is equal to this divergence term. And then the acceleration, it's just pressure gradients and viscosity and gravity and so forth. So these are the equations we're going to use. And then we recast them in particle form. Now there's a little bit of a trick to this. So we take our weighting function and multiply times the equation, integrate over the domain, evaluate boundary condition. And you can write it in this form. So I didn't show you that, but what we have is for each particle, the mass doesn't change with time. So that's one equation. We don't have to do anything with that. The particles are going to move with the velocity of the fluid. So each particle's position will change with time depending on the velocity. The density will change because of the conservation of mass equation, but it depends on this analytical function, right? And then the acceleration of each particle will depend on pressure, which looks a little bit different than in this form, but you have to trust me that this comes out of the math. So this is the pressure gradient term. This might be the viscous term, but again, it's analytical gradient here. So that part's pretty nice. So for each particle, we've got an equation. We have to solve these three equations, and the problem is solved. Needless to say, if we have lots of particles, we've got to time step each particle, so that's a lot of computations. Now, pressure, it's compressible fluid, so we use an equation of state. So we relate the pressure to the density. If gamma is 7 here, that's what you can use for the ocean, the full depth of the ocean. You use the density, say this would be the surface density, so you have this normalized density. The 1 is here to make sure the pressure is 0 at the free surface. And then we have this factor B. So now I can relate density to pressure. Given that form, I can calculate the speed of sound in my fluid. It's a compressible fluid, so it's got a speed of sound. Well, that's a bad thing because I'm doing water waves. Everything I'm going to talk about today is either dam breaks or water waves. The speed of sound is really fast, and the speed of a water wave is relatively very slow compared to that. I'm doing numerics, so the speed of sound is in my problem, so I have to do my time stepping according to the speed of sound. And it's so fast, that's a real problem. So if I want to do underwater acoustics, I have to take time steps that are 10 to the minus 6, 10 to the minus 7, really small time steps. But I really don't care about the speed of sound if I'm doing water waves. There are very few cases in water waves where you care about the compressibility of the fluid, impact problems and so forth. I might care about it. But in general, if I'm just propagating waves, I do not care what the speed of sound is. So I take this factor B and I adjust this relationship to slow down the speed of sound such that I don't have to time step so fast. So I artificially change the speed of sound. Doesn't do anything to the physics of the problem unless I make the speed of sound so slow that my water turns into jello or something like that. And I have to have the speed of sound be 10 times faster than any velocities or wave speeds in my problem. And if I do that, then the problem's okay. So I can speed down the speed of sound. I can slow it down a lot, but I can't go any slower than 10 times any velocities in my model. But as long as I do that, I'm okay. And that gives you a couple of % of compressibility. So I said there was open source code in 2007. We released SPH. This is the web page about it. And then January 2010, the second version was released. There's serial and parallel versions of the code. There are a lot of test cases and so forth that go with it so you can see how it works. So you get things like this. This is a dam break problem. So here's a dam. You're going to remove the gate, and then there's water in front of the dam. And you get comparisons to the data that look like this. So this is the development of the wave as the dam is removed and it propagates the flood water into the still water. And depending on the depth of the water, you can generate a plunging breaker of different shapes. And if it's really deep, then you generate a solitary wave that doesn't break, as you see in this picture. So this is the tailwater in front of the dam can be deeper and deeper and deeper, and the wave you generate depends on the water depth, as you might expect. Yes.
Is this a 2D or 3D?
This is all 2D right here. We'll get to 3D soon. And then early on, we did some, this is 7 years ago practically, looking at solitary waves running up on a beach. So the green dots are SPH and the blue dots are simulations in a Caltech laboratory for solitary waves rushing up a beach by Sinolakis. And so this just shows that you can get the solitary wave. This is your tsunami, rushes way up onto the shore and then draws back down and creates a hydraulic jump as it goes back down the slope. And we're catching that quite well. So that gave us some confidence that we can do some wave motions. And so then we said, well, let's look at more sophisticated phenomena. Let's look at splash up. So one of the things about splash up is that when you have a wave at a beach, and you've probably all seen this, the wave breaks and then it splashes up again. And you get this white water in front. And it actually can happen several times. You can also get things like fingers. So if you look carefully at the back of this wave, it looks like there are a bunch of vortex tubes curling over like that. And so where do they come from? Waves theoretically are irrotational, and of course there's turbulence and vorticity, but where do they all come from? And then this is some think, field data from Kubo and Tsunomura. Here's a wave coming to shore, it breaks, and then it breaks backwards. Just kind of a weird phenomena. So what happens when you do SPH? So this is SPH. This is our first stuff we were doing. This is 2006. And this is part of a wave tank, and you can see the wave breaking. Now it's very coarse because you can see all the particles. But the interesting thing with what you saw is that there's a plunging breaker, there's splash up, and then there's reverse breaking. So all of the phenomena that we were looking at. And then down here was the vorticity associated with a wave. So in 2006 we said, well, okay, they start to look like real waves. So you need more resolution. So this is some work by Ben Rogers, who's at the University of Manchester and was a postdoc with me at Hopkins. And so this is colors, pressure. You see the splash up, the second splash up, and the wave runs to shore. So, you know, we've got a wave maker, a wave tank, slopes, and so it looks like real waves. But kind of small. This is some work recently done at North Carolina State University looking at floating bodies and wave energy devices. And yeah, you know, you can use it. It's poorly resolved, right? So you can see all the individual particles, but, you know, it sort of looks good. So this is physics. But let's look at the science problem with this bouncing jet. You had a wave, it hit the water, bounced up, bounces again, bounces again. Well, that's just wrong, because jets don't bounce. So in the fluid mechanics class, you have a jet hitting a flat surface, solid surface, and the jet hits and it runs in this direction, and some of it goes backwards, but it does not bounce. If you have a jet hitting fluid, it penetrates, it does not bounce. So with waves, we have a jet of fluid hitting stationary fluid, but it bounces instead of penetrates. And so what do you need to do to make a wave bounce? And so we want to study it. Now the problem is that if you're using serial code, this takes a long time. So even with my slowed down speed of sound model, I have time steps of 10 to the minus 5 seconds. So I got to do a lot of computations. And on a serial PC, you know, it takes a month to do a bunch of waves in a wave tank. And so my lack of attention span is such that waiting a month is just too long. And so the question is, how do we do something faster? And also, we need a lot more resolution than everything you've seen. We need millions of particles, not tens of thousands of particles. And so some of you know about GPU computing, but if you look with time, and this only goes up to 2009, and you look at how fast CPUs are increasing in speed, and then you look at how fast massively parallel graphics processing units for gamers, you know, how fast that's advancing. This is single precision calculations, but it's going super fast compared to CPUs. And so I used to think gamers are, you know, slackers and, you know, not providing much value to the world. But in fact, you know, they're forcing the graphics companies to provide some really nice hardware. And so then the question is, can we use the graphics cards? And people have, in about, well, in the mid-2000s, we're using graphics cards for computations, but it was very hard to do because you had to know the language of computer graphics. You had to know what are warps and weaves and textures and all these things that people do for computer graphics. And people managed to wade through that and get numbers. You know, they could use these cards to compute numbers. But in 2007, NVIDIA released CUDA, which is a C++ kind of language with extensions that allowed scientists to get access to the graphics cards and do computations using C, which, you know, a lot of people are familiar with. So that was a big breakthrough. And the interesting thing is, you know, for NVIDIA, there's not much in it for them in the sense that you know, when you look at the scientific computing market, and then you look at the gaming market. So scientific computing is like this, and gaming is like this. So the fact that they talk to scientists at all, I give them a lot of credit, because we're money losers for them. But I think I'd like to show this movie, if it works. Just, it's going to take a minute or two, but you know, for those of you that don't have a good feel for how we compare serial processing to parallel processing. So the Mythbusters did this for NVIDIA. And so what he's doing is so what's happening is you know, each cycle of this paintball machine is drawing a dot, making a, well, you see what it's making. So we can think about how long it took to do that. And, you know, you get a nice smiley face out of it. So now we do it with a GPU paintball machine.
Specifically addressed paintballs in 1,100 barrels. Ladies and gentlemen, Leonardo.
One clock cycle. So 1 second to get to do it in slow motion. So I think you get a feel for serial computing versus parallel computing. So the idea is, let's use the graphics card. The graphics card doesn't have a lot of memory on it, so that's a limitation. But if you can run your job on the graphics card, then it's a massively parallel card. You can do an immense amount of computation. You can do so much computation that sometimes when you're coding up things, you say, well, you know, if I do this in a really clever way, I can cut my computations in half because A interacts with B, and B has equal and opposite, so only do half of it. But with GPU, it takes too much time to decide if you're on A or B. Do it all, and it's still faster. So it's massively parallel. You can get a lot of computation, even if you have to do it twice. Just throw away what you don't need. So I met Alexei Hero, who was doing volcanology in Italy at the time. And he basically took physics and put it on the graphics card. And when I saw that, I said, well, this is somebody I need to be friends with. And so you can see, very shortly I became friends with Alexei, even though he's a volcanologist. So the point is that this is kind of ubiquitous supercomputing. GPU cards are around. They're different flavors. NVIDIA has CUDA, but there are things like now OpenCL. There are other things that will talk to graphics cards for scientists. But since I didn't know CUDA, I'd stick with that. And so I use a Mac Pro laptop. So this has 48 processors in it. So I have a small computer cluster in my standard off-the-shelf. This is one generation old. The new generation uses a different graphics card. It's not NVIDIA. So you have to be one generation back until they go back to NVIDIA. But so, you know, it's a cluster. I have a cluster. I can do about 250,000 particles on my laptop and do nice problems. But then there are, NVIDIA sells Tesla cards and Fermi cards. The Fermis, the have about 480 processors on them. They've traditionally doubled every 18 months, and so we're close to a doubling, and so should be 1,000 processors in one card. That might cost you $4,000 or $5,000. That's the scientific card with 1,000 processors. So we're talking maybe this fall or something. 1,000 processors that you put in your workstation on your desk, or you can attach. They can put them in boxes and you attach them to your laptop and do your graphics. So 1,000 processors. There's not a lot of memory. That's the drawback. So in a cluster of 1,000 CPUs, you can have a lot of memory. But if the problem works, this is a really cheap, fast, super way to do it. So this is one of the things Alexei was doing. It's called GPU lava. So this is Mount Etna. It's erupting. Alexei lives down here someplace. I think Mount Etna is erupting right now, as a matter of fact. So he wants to get the modeling of the lava flows correctly. And so these are particles of lava being ejected. They flow down. This is temperature away from the vent. And he actually has solidification. So he's doing the chemistry and thermodynamics as things are going on, as well as the flow. Some of our early stuff with physics, we looked at a dam break hitting a building. And so this is what we got with about 30,000 particles. And with GPU, we could do many more particles and do it much, much faster. So this takes, like a month. This takes like a day. And the resolution matters. So here you can see when we have a few tens of thousands of particles, we have a dam break wave rolling up some water, smacking it into a building, and you can see the wave. But now you can see the run-up. So here you can see the run-up on the front. And then sometimes later, the water hits the back. I'm sorry, this is turned around, but it goes past the structure, hits the back, and makes a wave. Now what you can see is it actually comes up into the corner like this big giant wave and splashes back in. And this looks funny because it's this jet now falling back under gravity into the water column. So resolution matters. So having a big Fermi card allows you to do that kind of thing. So this is the code. I won't spend any time talking about that. In terms of CUDA, so it looks like C. And the only thing I want to say here is that the big trick is allocating memory on the CPU, allocating space on the graphics card, copying from the CPU to the graphics card. When you get done, bring it all back. And you do it, ideally you do it just once. You want to leave, whatever you're doing, you want to leave it on the graphics card. There's a cost to go back and forth. It's cheaper to stay on the graphics card and move data around on the graphics card. Bringing it back and forth between the CPU and the GPU is not a good thing. So you can't use it like a math coprocessor. You can't have a do loop, and every time you get a do loop, you go to the GPU, because you have to take all your data, pass it up to the GPU, do your calculations, send it all back, do some more stuff, send it up, send it back. It's very costly. You want to leave it there. And the way you do that is so here's a case where we allocated an array, and we're going to add 1 to every element of the array. And we want to do it on the GPU card. It's going to be massively parallel, so we want every processor doing this addition to all of the number of particles we have in or this matrix anyway. And this is what you have to do, and I'm not going to really explain this, but basically that's the whole of the massively parallel thing. These things, some of these you provide, some of these things the card provides, but basically this is a do loop that says add 1 to every element of an array that we've passed up to the graphics card. And so all that parallelization is taken care of by the card in CUDA. So now let's get back to the science question. Do jets bounce? So here's a case where this is 2D SPH. This is now GPUSPH. So here's a jet hitting water, and it penetrates. So it creates a cavity. The cavity closes onto the jet. It penetrates. No bounce. So that could be like a wave jet. It doesn't bounce in this case. It's stationary jet. So Jim Duncan and a student at University of Maryland said, well, maybe we need to move the jet. Let's translate the jet and see if we can bounce a plane jet. And so this is all elaborate carriage arrangement, and it has special ways to cut the jet, and so that basically what he gets is a clean jet into still water that's moving at a certain fixed speed. And so these are the kinds of stuff that he's gotten. Basically, he's moving this jet at 15 centimeters per second. It's impinging on the water. You can see it creating a cavity. Here's the jet. And then it pinches off like I had in the simulation. And then you get all this funny behavior. No bounce. And it pinches off in part because the cavity closes on itself. Also, the jet is moving, so it runs into the side of the cavity. So this is my simulation of exactly the same thing. It looks similar. We have comparisons to data that look quite good. The interesting thing is, if we look at time to pinch off, which is what he measured, we get good agreement. But then, of course, he can't move his cart any faster than about 50 centimeters per second. Since I'm doing it numerically, I can move it as fast as I want. And what you find is pinch-off times change depending on the speed. And also the pinch-off depth. How far did the cavity get created? And so we get good agreement. But then I can go faster and faster. And here, there's no depth. It's positive. So what's going on? And so this is kind of what's going on. You have to move the jet really fast to bounce it. And it turns out, as you'll see in this picture, there is the solution by Milne-Thompson for intersecting jets. And if you manipulate the solution right, and if you tilt your head to about like this, and imagine this is the water surface, this is the impinging jet, and so you have a jet of speed c, and then you move the whole system at speed c, so you got speed c this way, speed c this way, the jet will bounce. Not only that, but it doesn't penetrate. So here's the water surface. Remember, you've got to tilt your head. Here's the water surface, and it bounces off this cushion, sort of water cushion here. So this is a steady state analytical solution, no viscosity and so forth. So the trick is you have a plane jet, you move it fast, it will bounce. And what it's trying to do actually is it's trying to penetrate, but it's moving so fast laterally it cannot do that. And so half the water goes this way and half the water goes this way. All right, so now let's look at other applications. So here's higher resolved waves on a beach using GPUSPH. Except for my Terminator-like colors, this looks like a wave at a beach, at least to me. You know, this is a wave maker here. The wave comes off fairly cleanly, but as soon as it breaks, and there's a little bit of bounce up, it's not very well resolved, but there's a bounce up. And you notice all this 3D structure, immense amount of 3D structure and turbulence. And you see all this scarring on the water surface because of all the vortices and so forth under the water surface. So this looks quite realistic. So that was kind of reassuring. And then Katrina happened, and so I came down here to one of the first engineering teams into New Orleans. And so the question is, what does a falling flood wall look like? And so I got kind of intrigued by looking at the advantage of SPH of doing that problem. So here's instantaneous failure of a flood wall section, 3 structures, and the advantage of SPH is, you know, you got immense splash up and run up on the structures, and you can model all of that because we don't have to worry so much about the free surface. The free surface is wherever the water particles are. A lot of methods, Eulerian methods, based on finite element, finite volume, you got to track the nonlinear free surface. And mine, it just goes wherever the water goes. So then you can do tsunami-like problems, instantaneous failure, on my laptop. I think I was doing it in an airport. And in 20 minutes, I can get this much of that problem done just on the laptop. So this is something recently we've been doing. So there's a wave maker here that you can't quite see. This is a floating object. So we're starting to do floating objects. Red means high velocity. And so you see a wave crest coming. Plunging breaker goes over the sphere. It bounces. It floats up through the base of the wave. But what's interesting is there is splash up. It's hard to see because we sort of washed out the colors. But there's a splash up. And then you can see an immense amount of 3D structure in the face of the wave. And so this is, looks like your Hawaiian kind of wave. So this just goes on and on. But what I'm kind of interested in is what's the turbulence under the water surface. And we're just starting to look at that. So one of the interesting things with SPH is that each particle moves, and you know which particle is which. You start out with, in this case, 3.25 million of them. They're all numbered, and as it moves, I know where it goes. So this is color-coded by the numbers. So particle 0 is here, and we get a bunch of numbers, and we get the second row, and each layer has a higher and higher number as we add up the number of particles. So particle 3,200,000, whatever it is, this guy right here is here. And so what you see as the wave maker is moving is that there's a drift of the surface water towards the shore, except where breaking occurs. And then the plunger that bounced left behind this vorticity. And it's spinning, and then it's going down to the bottom. And so now we're to the point where we can start doing some Lagrangian calculations of coherent turbulent structures. But you notice splash up. Now this is 3D, but we took the wave tank and we cut it in half. So we're looking at the middle slice into the 3D structure. But you notice that there's some mean flow here because this is all blue water at the top now. It used to be red, and so the bottom water is being pulled up at the wave maker and moving along the surface. So there's a circulation in the tank. And so, with a few more waves, a little bit of averaging, we can draw the mean flow in the tank from startup conditions. And what we're just starting, and in fact, my student just sent me this last night, so it's lambda 2 criteria for coherent turbulent structures. So you notice that we have these structures. So lambda 2 criteria is basically taking the gradient of the velocity, separating it into a rate of strain and rotation, and plotting the rotation. And basically, so these are regions of high vorticity and low pressure right in here. And so, since this is hot off the press, it's hard to interpret it. But basically, what we know is we have these rollers of turbulence in here, and in the y direction into the board, they're very irregular. Right? So these are not nice, smooth cylinders of vorticity induced by this plunging breaker, but there's a lot of 3D instabilities going on. And so this is what we're getting ready to look at. This is a different application, some very simple, less number of particles, waves, so, vegetation in the surf zone, or piling or something, but so they happen to be cut off. This I did trying to impress somebody one afternoon, just putting him in because she was interested in piling in the surf zone, and so I did it. But what was interesting, and she was impressed, but what was interesting was that if you look at the water line, so we have some startup issues, but okay, so here's the still water line, and then the first wave comes, and all of a sudden it moves, and it stays up. So this is wave run up and wave set up, and because there's a momentum flux in the waves, and that here there's no momentum flux because the waves are all broken, we need a hydrostatic force to balance that. And so we have a setup of the water. And so then I started thinking about, well, what else can we do? Setup drives a lot of things in surf zones, like rip currents. And so the question is, can I do rip currents using SPH? So I've convinced myself I can do waves really well, but waves do work on the surf zone and cause mean flows and all these kinds of interesting things. So can I do that? So do I get the means right and so forth? So we looked at an experiment done in Denmark by Dronen. There's a wave paddle over here. This is a tank that's got sidewalls. And then right here, as the water's coming up, or the beach is coming up, we have this fake sandbar. It's kind of artificial. But it's a shallow section and a deep section. So this is a rip channel. This is a sandbar. So here's our simulation. I seem to be doing things just in time. So this was the night before a conference presentation, and I got this movie, and I was kind of ecstatic because it showed, first of all, it showed a lot more than I expected. And so I'll try to convince you of that. So here's the wave maker. It's creating waves. They're very long and linear, as they should be coming off the paddle. The shallow area is right in here. So the waves are breaking. You can see just incipient breaking here, breaking all through here. And then a lot of interesting things happen. So the wave comes across here, and then all of a sudden you see these high frequency things. So there's a nonlinear resonance of shallow water waves that they will separate into harmonics, and it's called harmonic generation. And so it looks like we're getting harmonic generation. So that was a surprise. The water comes in, waves come in here, raise the water level here on mean. That gives a gradient in this direction. The water goes out the rip channel that was there. But look, the wave crests are all bent here. So there's wave current interaction. So that outgoing flow is slowing the incoming waves. So now I got wave current interaction. So I've got wave breaking, wave refraction and diffraction because of the depth changes. So you got diffraction and refraction going on. So wave breaking, wave refraction, wave diffraction, wave current interaction, harmonic generation, set up, run up. There must be a couple more, but anyway, I was really ecstatic when I saw that. So it looks like what you'd expect in a real surf zone. These are the mean flows. So we calculated from our Lagrangian method, we calculated the Eulerian mean flows, and what you get is a rip channel here. You also get a second circulation inside the surf zone. This is Dronen's data. Unfortunately, they threw their data away, and so we just had a paper to deal with. So we had these arrows to compare with from the paper. Experimentalists, don't throw your data away. Somebody wants it. And so we see some evidence that, you see this is going this way. There's a little bit of evidence of this circulation cell, but a lot more of this circulation cell. So we don't have much to compare with in this particular case. And of course, we can get 3D structure to it. But then we started moving on to a different problem. So I said I had a short attention span. So, so Rosita's doing this, so I let her do that. So the question is, what happens when you have a space capsule smacking into water? So this is supposed to be a representation of the new Orion space capsule, which comes in on parachutes. And if the wind is blowing, then it'll hit the water at some pretty good velocity, downward and horizontal. It's not good for the astronauts if it comes out upside down. So the idea is this capsule should have the pointy end up when it's done. In this particular case, the pointy end is down. And so that's not good for the astronauts. They're planning to blow balloons at this stage, and the balloons should flip it back up. So we're just starting some work doing this kind of impacting problem. And to finish up, the code is open source. The GPU code, this is GPUSPH. On the web, it's available for CUDA 3.2 version. CUDA is at 4.0 right now and going to be 4.1 pretty soon. We have a version of the code that's 4.0 that will be up there now, but we're running CUDA 4. It's available if you want to try it. What are we doing? Well, at present, we've got, I talked about NVIDIA and its Tesla cards and Fermi cards and so forth. I'm just using single cards. The code now will do multi-GPU. We don't do multi-machine. So one of the things we wanted to be able to do is have one machine with a lot of GPU cards and another machine with a lot of GPU cards and link them all with MPI and then do multi-GPU on each machine. We have a new machine that's just been built at Hopkins, which is has 100 Tesla cards in it. So the idea there is, I have more cards to do. I can spread the computations out over more cards, but I also get more memory, so I can do more particles by just distributing the problem, because each card, I think, has 3 megabytes. So I can do bigger problems, but also do them faster. And so that's what we're working on now. We're working on multi-fluid problems. So I want to be able to do air. Right now, all you see is water. We can do 2 fluids if we put a lid on it, but we're working on multi-fluid, being better at that. You saw some fluid structure stuff. Some issues with boundary conditions. We can't do boundary layers very well. But I think I've convinced you that GPUSPH is good for waves and some fluid problems. Bouncing jets. The plane jet has to be moving fast to bounce. You cannot bounce around jet. So because the plane jet bounces this way, so half the water is going backwards, half's going forwards. So if you have a plane jet, you get another jet. If you have a circle, then you just spray in all directions, and you don't get a bounce. So it's only for plane jets. So waves are make nice plane jets. And I think I've convinced you of the first one anyway. So that's it. Thank you. Two minutes to go. And it did vibrate, by the way.
Now we have 10 minutes for questions.
Sam.
So you say we've got the problems with boundary conditions. It's not a post-boundary layer analytical tool yet?
Yes. So I can do slip and non-slip boundary conditions. But the problem is, I either have to do, I've got these big blobs of fluid, right? And so unless I if I just care about the boundary layer, then I can do it, because I'll just make my particles really tiny and get a whole bunch of them inside the boundary layer, and then I'm done. But if I'm doing a problem like that ball floating in the wave, and I really cared about the boundary layers, then I have this problem, because my particles are big and my boundary layers are small. And so if I do nice angular objects, where the flow separation is pretty obvious, I think things are pretty good. But if I do cylinders, I think where the flow separates is going to be wrong because of the boundary layer. And so in astrophysics, they use variable size particles. And so I think that's a case where we've got to move to that. And it turns out it's not that hard to do, but we just have not done it. So I think right now, boundary conditions are a problem in the sense that you have a lot of choices of boundary conditions, and some are more sticky than others, and people have favorites. But I think the boundary layers are the problem, and so far I just don't pay any. I forget about them, not worry about them. But I think if you're trying to do like sand in a channel, or rolling rocks or something, that the boundary layer is going to be important. Yes, sir.
Is there a way to quantify how your solution improves with particle densities?
Yes. So, for instance, on that rip current study, what we did was just do a whole bunch of different particle sizes. So we just made them smaller and smaller till it stopped. The answers stopped changing, and we said, okay, we're done.
But you don't have like a theoretical that should converge at such and such a rate?
No. it's all regularly spaced and things like that. So, nope. Yes, sir.
In some of those movies you showed, it looked like you had rendered the surface, but to visualize it,
Yes.
did you have to extract the surface?
So we have surface extraction techniques now, but that was done before the surface extraction. And the two really cool, artistic-looking ones, I took my data files and I shipped it to a guy who used to work in Hollywood, and he works for Templeman Automation, and so he detected the surface and drew the surface. So I'm not quite sure how he did it. He used software called Houdini, and it looks pretty good. But we actually now have new features in the model where we can ask for surface particle position, so you get the surface layer, and that works pretty well. In fact, very well. And the other thing is we have a thing called test particles, so we can put in Eulerian points. So the problem is this is a Lagrangian model, so all the particles are moving, but we put in fixed points, and then we sample, do that SPH averaging and at fixed points, and so we get data files that are measurements at a point. And the next thing we're going to do is have a wave gauge, so you say, I want to know the water surface behavior with time at a fixed point, and so that'll be the other measurement particle we have. Yes, sir?
Did you have used for a real-life problem?
Yes. Those are all real-life problems.
But real scale, I mean.
Yes.
Even number of particles?
No, they just get bigger. Yeah, so, I mean, I can do, so, you know, with a 100 GPU machine, I can do 100 times 5 million particles. So I have that feature, just use a lot more particles, or I just make my particles bigger. But, you know, that you can get away with that for some problems, and, you know, if boundary layers are important, maybe I can't. So I think it's all going to depend on the problem, and you know, maybe you have to do variable size particles or something like that. But you know, I have small ones near boundaries and bigger ones further away, which that would make sense. We just have not done that. I should say we also do. We have an LES viscosity, so we can do laminar viscosity, LES, very simple LES viscosity. We're working on dynamic LES right now, so we have better viscosity models. There's work going on in France with better boundary conditions done by the French. We're doing the multi-fluid and the multi-machine. Okay. So those are going to be done in the next year or two. Yes, same.
So what about open boundary condition like literature, where you've got a
We can do periodic boundary conditions, and with the lava flow, that was a vent, right? So we're producing. What we're trying to do now is do a high-speed vent, so we have to have a continual influx of particles, and we haven't worked that out yet. But for channels, we have the periodicity. So you know what comes out this end, comes in this end. So that works right now. So that's how we test the lava, by letting it free fall down the mountainside and look at velocity profiles. For lava, the boundary layer works out pretty well. It's so viscous. Yeah.